Hi, my name is Óscar and I'm going to explain the parallel RLC circuit. In a parallel RLC circuit, the resistor, the inductor, and the capacitor are connected in parallel to each other across a voltage supply, in this case Vs. As we can see in this circuit, Vs is common to all three components, whilst supply current Is composed by three parts. The current at the resistor IR, the current at the inductor IL, and finally the current flowing through the capacitor IC. That said, the current through each branch of the circuit will vary as it is different to each other and to the supply current Is. Since the voltage across the circuit is common, the current in each branch may be found by using Kirchhoff's law in node A. Kirchhoff's law states that the total current entering a junction or node is exactly equal to the current leaving that node. Therefore, we have equation number 1. However, even though this equation includes all of the components in terms of current, it would be convenient to take advantage of the fact that each of the three basic components, resistor, capacitor, and inductor, can be described in terms of the relationship between the voltage across and the current through the component. For example, in the case of the resistor, the current voltage relationship is given by the Ohm's law, which led to equation number 2 that indicates that the current equals to the voltage over the resistor. In the case of the inductor, this same relationship is given by equation number 3, that states that the current equals to 1 over L times the integral of the voltage with respect to time. And finally, for the capacitor, the current voltage relationship is given by equation 4, that states that the current equals to C times the derivative of the voltage with respect to time. Therefore, by substituting equations 2, 3, and 4 into equation number 1, we could write equation number 5. This equation describes the system's total current as the sum of the current voltage relationship of each of the components in the circuit, which upon differentiation and division by C becomes equation number 6, in which all of the terms are given by the derivative of the voltage with respect to time, where V of t is the voltage across the circuit throughout time. This second order differential equation describes the behavior of the circuit. Additionally, the fact that it is a second order equation is explained by the two reactive elements in the circuit, the inductor and the capacitor. For solving this ordinary differential equation, we will assume that the solution are the exponential form, as the first and second derivatives of the function have the same form as the original function. Therefore, p of t equals to a times the exponential of s times t, in which both a and s are constant. Then, by substituting this solution into equation number 6, which describes the behavior of the system in terms of s, we have equation number 8. However, if we divide out the exponential in equation number 8, it is possible to obtain the characteristic equation for the system given by equation number 9, for which the general solution is included and described by equation number 10. However, if we reduce equation number 10 considering the parameters given by alpha and omega, the general solution is narrowed to this equation right here. However, the type of system is determined by the discriminant, for which there are three possible cases. In the very first case, alpha is greater than omega, therefore the discriminant is positive and the roots are real and unequal. This causes the system to be an overdamped system, which is described by the red line in the graph. In the second case, alpha and omega are equal, therefore the discriminant is 0 and the roots are real and unequal. This causes the system to be a critically damped system, which is showed in the graph right here. Finally, the last case is happens when omega is greater than alpha. Therefore, the discriminant is negative and the roots are complex and unequal. This causes the system to be an underdamped system, which is shown by the blue line in the graph. Let's now explain the response of resistor, capacitor, and inductor to an applied sinusoidal voltage, which corresponds to the situation seen on the circuit previously examined. For the resistor, the observed behavior can be explained since the current at any point on the voltage curve is predicted by Ohm's law, so the current is always proportional to the magnitude of the voltage. Consequently, there is no phase shift or frequency dependence for the resistor circuit, as seen in the graph. However, if we consider that the relationship between the current flow and applied voltage in a capacitor is given by this expression, if the voltage has the form of a cosine graph, the current at the capacitor will be described by a sinus graph. Therefore, the current going through a capacitor and the voltage across the capacitor are 90 degrees out of phase, as seen in this graph right here, in which the voltage is described by the red line and the current is described by the green one. And finally, for the inductor, the relationship between the current flow and the applied voltage is given by this expression. Therefore, if the current has this form, the voltage will become a sinus graph. Therefore, as seen with the capacitor, the current going through an inductor and the voltage across the inductor are also 90 degrees out of phase, as seen in this graph, in which the voltage is described by the red line and the current is described by the green line, in which it is possible to see the difference of both graphs.